Hello, class. Today we're going to do some more z-test problems, and then we're going to talk about assumptions of parametric test. All right, so it's that time of the year again, the time of the pumpkin spice latte. So this question talks about a law that New York City enacted, and they enacted a law that required all chain restaurants to post the calorie counts for all of their menu items. And these researchers, Bollinger et al. In 2010, wanted to see if this would change the drink consumption of customers at Starbucks. So beforehand, they calculated the population mean of everybody that went into Starbucks, okay? And they found out that the population mean of the calories consumed per drink, okay, was 247. Okay, so 247 calories consumed per Starbucks visit with a population standard deviation of 201. Okay, they went to a ton of Starbucks and were able to come up with what the population mean was. This is actually an example in your textbook, if I remember correctly. All right, so after this law was enacted, they go and they collect a sample of 1,000 individuals at New York City after the calorie counts were posted, and they found a mean of 232 calories consumed per visit. The question is, do customers visiting a Starbucks on average with the calories listed on the menu consume a lower, emphasis here on lower, number of calories on average than customers visiting Starbucks without the calories listed on the menu? So we're comparing the sample of the number of calories consumed per Starbucks drink after the law has been enacted and comparing it to the population mean of the number of calories consumed per Starbucks drink before the law has been enacted. And is there a statistical difference between these two? Okay, just like before, we're going to write out all of the relevant aspects of this problem. So we've got 1,000 subjects in our sample. The mean, notice my little subscript here, is 232. I could have wrote X bar after, or I could have said, instead of after, calorie count on, or something along those lines. But it's whatever notation system I want to use when I'm doing this problem. All right. The population mean beforehand is 247, and the population standard deviation is 201. And I did not give you the population variance, but I could easily calculate it by squaring this number right here, squaring the standard deviation. And sometimes I might do that just to give myself all of the data in case I might need the variance for the problem. This is a one-tailed test. Why is it a one-tailed test? Well, here we have the prediction. Do customers visiting a Starbucks with calories listed on the menu consume a lower? Lower denotes that we have a hypothesis. We're hypothesizing that the number of calories is consumed lower after the change, as opposed to, we're just seeing if there's a difference. So if I see lower or fewer or greater or more, any of that when I'm asking this question, it's a one-tailed test. We have a hypothesis about what's happening. We have a directional hypothesis, I should say. All right, so we've got a one-tailed test, and that's going to be the different part here. So let's go through our 4 steps. First of all, we're going to state the hypothesis. And what I have here, I've got all the different permutations that we could have used to get this, but notice here that the alternative hypothesis, the mu of after, the population mean of after, because again, we care about population means, we don't care about the sample means, is less than the population mean of beforehand. All right. Notice that the alternative hypothesis is just mathematical notation of what's right here. All right. Do customers visiting Starbucks with calories listed on the menu consume a lower number of calories than Starbucks visiting without? So the population mean afterwards is lower than the population mean beforehand. And that's what I have right here. The null hypothesis is always the exact opposite So I have to switch. Instead of less than, it's greater than. And like I said before, there's always an equal sign in the null hypothesis. So we have greater than or equal to right here for the null. Of course, we know that the population mean is 247, so we could plug that in if we wanted to write our null hypothesis and alternative hypothesis that way. I've mentioned it before, but another name for the alternative hypothesis is the research hypothesis. Just make sure that you know that those terms can be used interchangeably. All right, what is the decision criteria? So what is alpha? Alpha for all psychology studies, for everything that you're going to do in this class, is 0.05, and we need to make sure that we state that. What kind of test are we doing? Well, we're comparing a sample to a population mean, and we have the population variance. And heck, the title of this lecture is One Sample Z-Test. Probably going to be a one sample Z-test. Is it a two-tailed or one-tailed test? It is a one-tailed test. So what this means, let me get my drawing utensils out. Here is our lovely sampling distribution. What the sampling distribution would look like if the null hypothesis were true. Now, we are guessing, we have a prediction that the population mean for when the calorie count is on the menus is going to lead people to consume fewer calories. So we need to find a cutoff value for our standard normal distribution. And that cutoff value, we will find that the number of subjects, the percentage of subjects here should be 0.05. All right, we're putting all of this 0.05 on one side of the distribution, because again, we're not just testing if there's a difference. We're testing if there was a difference. We'd have to put half this rejection region over here, half the rejection region over here. Since we have a directional hypothesis, we can put all of our type 1 error on one side of this distribution. So what is the special value, the z-value right here, that if we have that z-value, only 5% of people would score lower than that just due to chance? Okay, let us go to our table and find that. Okay, so going to my standard normal table, and I'm going to have to look at things a little bit differently since all of these values are positive and not negative. I'm going to look for when the smaller portion, okay, is 0.05. So I'm looking, I'm not seeing it, I'm looking at the smaller portion, it's getting smaller, but I'm looking for when it hits 0.05. And lo and behold, this is where it does it, okay? This is at least the closest here, all right? So when we have a z-score of 1.64, that means that roughly 5% of people are going to score above that z-score. But since the standard normal distribution is symmetric, I can also tell that the z-score of negative 1.64 will let me know that about approximately 0.05 or 5% of people will score less than that. Okay, I'm going to be a little bit more exact. And say that the cutoff is negative 1.645. This is another value that I want you to know. All right, so if we have a one-tailed test, the cutoff, if we're testing if something is greater than, more than, whatever, is positive 1.645. Always, always, always. It's just the way that a normal distribution works. If we have a hypothesis that something is less than something else, well, it is 1.645 as well, but it's negative 1.645. All right, those values don't change. Again, this is the way that the normal distribution is. And if we keep our alpha consistent, these are what these cutoff values are going to be. So our cutoff value is negative 1.645. So do we reject the null hypothesis if our test statistic value is greater than negative 1.645 or less than negative 1.645? Sorry about that. Our cutoff, we're going to reject when our value, our z, is less than this negative 1.645. right? It wouldn't be the other way around. We're very likely to get a z-score that is more positive than that, okay? So if we get a z-score, if our z-test statistic is less than negative 1.645, then we reject the null hypothesis. And if z is greater than negative 1.645, we're going to fail to reject or retain the null hypothesis. Now, these two parts down here I've included for you guys. You don't necessarily need to include them in your step 2. If you include everything, these 4 lines right here, you're perfectly fine. I'm just showing you this because sometimes people get confused about when to reject and when to retain. All right, let's do the math. Okay, here is the formula for our z statistic. All right, we need to find the sample mean, which I believe was 232, minus the population mean, which I believe was 247, all over the population standard deviation, which was 201, and then over n, the square root of n, which should be the square root of 1,000. Am I correct? I think I'm close. Or maybe I did it exactly right. I don't know. All right, so it's just plug and play at this point in time. All right, we do the math, and we get a z-score of negative 2.36. Is this less than our cutoff value? Again, we want to make sure that we are comparing this to our cutoff value. And the answer is yes, it's less than negative 1.645. So we are indeed going to reject the null hypothesis. Okay, how do we write out step 4? We reject the null hypothesis. That's the first thing that we need to write. Do we reject or do we retain? We reject the null hypothesis in favor of the alternative. So now we need to explain the alternative in English. That the population mean of calories per Starbucks visit after the law, and I include the mean here, is less than before the law, and I include the descriptives there. Why don't I have the descriptives here for standard deviation for the sample? I didn't provide it for you, and if I don't provide it for you, if you don't have it, you can't write it in here. Okay, so just provide as much evidence as you have for these write-ups, these step 4s. And now I'm going to talk about what the statistic is. Z equals negative 2.36. And we know if we reject the null hypothesis that the p-value, the probability of obtaining these results, given that the null is true, or results even more extreme than this, it has to be less than 0.05. Mind you, if we did this in SPSS, we could get the exact p-value. So this would work perfectly fine. Now, if we talk about things in terms of population means, we are just trying to see if there is a difference. All right, but if we talk about things in terms of a sample mean, we reject the null hypothesis in favor of the alternative that the sample mean of calories per Starbucks visit after the law is significantly less than before the law. Okay, we need to make sure that we include that significantly if we're talking about things in terms of sample means. We talk about population means, we just care about, is there a difference, or is it less than or greater than this? We don't care about if it is significantly less than, okay? Because ultimately we're inferring about the population. But a sample mean, our eyeballs can tell us that there's a difference. We care about if the difference is of such a large magnitude that it leads us to the decision that in the population, those two population means are different, or one's less than the other or greater than the other. All right, so hopefully you're getting the hang of things. Let's do one more. This is kind of a dumb problem that I came up with. Across the USA, the average number of children that a person has is 2.3. I've completely made this up. I don't know if this is true. The variance is 3. So we've got a population mean and we've got a population variance. We interview a sample, so we've got a sample now, of 40 people in Dahlonega to see how many children they have. They have an average of 2.5 children with a variance of 3.1. So now we're going to do our one sample z-test to see if there is a difference. A difference? No, not a difference. Does the population of Dahlonega have more children than the average USA family? All right, more, what does that tell us? We've got a directional hypothesis. We need to do a one-tail test. So let's write all the information that we have. First thing that we have is the population mean of 2.3. Now we have the population variance, and I can convert that easily to the population standard deviation for all of America, subscript USA. Our sample size is 40. Our sample mean should be 2.5. And our sample variance here is 3.1, and I can easily convert that to a sample standard deviation if I want to. All right, so let's go do the problem. Let's do the 4 steps. Oh, and I know this is one tell because it's more than. State the hypotheses. Well, notice here that does the population mean for Dahlonega have more, so I'm going to do a greater than sign, the average USA family, population mean for the USA. So my alternative hypothesis should be mu of Dahlonega is greater than mu of USA. Let's see if I did it right. Oh yes, I did do it right. I did it a little bit differently. Instead of doing the mu of USA, I did it in terms of 2.3 because I know what the population mean is. This is a perfectly fine way of doing this. But notice that my prediction is greater than, okay, because I said more than in the problem, have more children. It's a good way of thinking about things. Also, I am getting less and less writing everything out. So as we progress, I'm going to take more and more shortcuts through things. Instead of writing the 20 million different ways that you could say this, I'm just going to pick one and do it. Okay, just for you guys to be mindful of that, because you will see that in the future. How about the decision criterion? Well, alpha is going to be equal to 0.05. We have a one sample z-test, as we can easily tell. We have a one-tailed test, as we mentioned previously. And the cutoff value, if it's more than, if it's a one-tailed test, it's going to be either negative or positive 1.645. Since our prediction is greater than, we are predicting the z-score is going to be higher than positive 1.645. So my cutoff value is going to be positive 1.645. Cutoff value is what I write. Some other people might write criterion value. Other people might write Z critical. Okay, you might see that as well. It's pretty much identical. Okay. Also notice here that I didn't write out what we're going to do when we retain the null hypothesis. I don't need to do that at this point. Okay, and again, you guys don't necessarily have to write this as well. But I know that if Z is greater than this value, we're going to reject the null hypothesis. If Z is less than this value, we're going to retain the null hypothesis. And again, let's draw our friendly standard normal distribution. Okay, we're converting everything to the standard normal distribution, remember. Now, if we're predicting that something's going to be greater than something else, we have to look at the right side of the distribution. All right, so this is our cutoff value, and this is our rejection region. If we find a Z anywhere over here, we are going to reject the null hypothesis and say that it's probably the case that the null hypothesis is not true. Remember, this value is positive 1.645. All right, and the probability, if the null hypothesis were true, that we would reject the null is 0.05. That is our type 1 error rate. That is our alpha. All right, just a little bit of review there. You can never have too much of that. All right, so we are going to calculate the test statistic and compare it to the cutoff values. I am going to take the sample mean, 2.5, minus the population mean, 2.3, and I'm going to divide it by the square root of the population variance, which is 3, over the sample size, which is 40. If I do this math, I get 0.730. Is this greater than 1.645? No. All right. So we are going to retain the null hypothesis. So how would we write this statistical conclusion? Well, we would say we failed to reject the null hypothesis. We could easily just say we retain the null hypothesis. Now we're going to explain the null hypothesis, that the population mean for the number of children people have in Dahlonega is equal to or lower than the national average. And then we have our descriptive statistics, we have our Z value, and P we know has to be greater than 0.05. If p was less than 0.05, we would have rejected the null hypothesis, but we retained it, so p has to be greater than 0.05. All right, if we want to talk about things in terms of sample means, we can say we reject the null hypothesis, or we failed to reject the null hypothesis that the sample mean for number of children people have in Dahlonega is significantly different or lower than the national average. Okay, okay, so that is good. Okay, so now I want to talk about some assumptions of the test that we're doing. All of the tests that we're going to talk about from here until the very end of class are called parametric tests. Parametric tests have specific assumptions about them. And if those assumptions are met, the test works perfectly fine and we are very confident in the conclusions of our test. But if those assumptions are not met, we have to be cautious about the interpretations of our test. So what are assumptions? Some assumptions are characteristics about a population that we are sampling that is necessary for accurate inferences. So these are characteristics of the population that we are inferring are true. And if they are true, our statistics work out fine. If they are not true, we've got to be cautious. Remember what your parents told you about assuming, right? It makes an ass out of you and me. If these assumptions hold true, we don't have a problem. If these assumptions are violated, if they don't hold true, sometimes we have a problem, sometimes we don't have a problem. We'll talk about these instances a little bit later on. So awareness of the assumptions for our chosen hypothesis is very important for us. So caution is important when proceeding with a hypothesis test when the data do not meet all of the assumptions. So we've got parametric tests. Parametric tests have specific assumptions about the population. And let's say that those assumptions are not met, or maybe we don't want a parametric test. Well, there are non-parametric tests. These are tests that we can use in case the assumptions for a parametric test are not met. What's the difference between these two? Typically, the parametric test is going to be more powerful. By powerful, I mean we're more likely to reject the null hypothesis. We're more likely to say that there is a true population mean difference if we use a parametric test. For the non-parametric test, there are no assumptions, so that's good, but that means that we're going to sacrifice power. We are less likely to reject the null hypothesis. So pretty much all the time, we would rather do the parametric test than the non-parametric test. But sometimes the non-parametric tests are the only thing that we can do. So what are some assumptions of a parametric test? There's 5 that we're going to talk about. There's not always 5. Sometimes there's 4. Sometimes there might be an additional assumption. But for right now, let's talk about 5 assumptions. The first assumption is that we have a scale level of measurement. So if we're talking about the scale of measurement, we have either an interval or ratio scale of measurement. Okay, we cannot do parametric statistics with nominal data. Okay, it doesn't work. We have to use a different kind of statistic for that. Maybe a chi-squared statistic, more about which much later on in the course. All right, we are making the assumption of random selection from the population. All right, the subjects that we have are supposedly a representative sample of the population as a whole. All right, so we need to be mindful of that. Okay, when we're generalizing about the population, we are assuming that the sample is representative, that we obtain the sample using random selection. 3, and this is one's a little bit hard to grasp. This is independence. The scores are independent of one another. All right, so let's say that we have some kind of experiment. Let's say that it's a statistics test, and somebody yells out the correct answers to the test somewhere in the middle. All right, now the scores are no longer independent of one another. Someone has said something, and that's impacting all of the other scores. Maybe, let's say that class is very similar to what we have now, where I have a third of you in one class, a third of you in the next day, and a third of you the last day. it might impact one cluster of you, but not all clusters of you. All right, so we need to make sure that all of the scores, all the measurements are independent of one another, and there's no residual relationship that somebody has yelled out the correct answer, or somebody's score does not impact anybody else's score. If that's the case, we cannot use a parametric test. In fact, we can't really salvage that situation at all. The scores need to be independent. All right, the next assumption is normality. If we look at the dependent variable in the population, we're making the assumption that the score is normally distributed in the population. All right, that is an assumption. We'll talk more about this assumption a little bit later on. The last one only applies in certain situations. All right, for a one sample z-test and for a one sample t-test, not a huge issue, but homogeneity of variance is the idea that the population variances between group 1 and group 2 are exactly the same. All right, if we have an experimental group and a control condition, we're assuming that in the population, those two variances are exactly the same. If there is a difference, this might lead us to make an incorrect conclusion doing our statistical analyses. This is going to be particularly problematic when we talk about an independent samples t-test. For a one sample z-test, one sample t-test, not a problem. Okay. All right. So what happens if we fail to meet one or all of these assumptions? So one option for us is to conduct a non-parametric test. And sometimes this is the best way to go, particularly if there's no way with the data type that we're working with that we can use a parametric test. We'll talk about some examples of these later on in this class. But if we don't meet all of the assumptions, we could still do the parametric test. In fact, most people would go ahead and do the parametric test. They just need to be cautious about the conclusions that they draw. They need to be mindful of the fact that they're violating these assumptions. Some of these assumptions are a big deal. Some of these assumptions are not a big deal. All right. So meeting the assumptions ensures that the quality of our research is 100% grade A, good, wonderful. If we don't meet some of the assumptions, that doesn't mean that our experiment is terrible. It might be the case that we can correct for this particular problematic with this assumption. So let's go through the 5 again and talk about what is problematic if we violate this assumption. So scale measurement. If we have nominal data, can't use a parametric test. All right. How about if we have an ordinal scale of measurement? It's a bit iffy. Okay. Most people would just do the parametric test. So you guys are familiar with the fact that Likert type scales, okay, rating yourself on a 1 to 7, it's an ordinal scale of measurement. And yet, in psychology, most of the time when people have a Likert type scale, they're analyzing it via a parametric test that makes an assumption of a scale level of measurement and not an ordinal scale of measurement. Somewhat problematic, but people do it all the time. We just need to be a little bit cautious about the interpretation of our results when that is the case, when we have ordinal data, because some tricky things might happen. Random selection. If random selection is violated, that is okay, but we just can't generalize our findings to everybody in the population. All right. So we need to be mindful about the generalization of our study to everybody in the population if we do not have a random selection of everybody from the population, right? I mean, this makes sense. When we use only college sophomores, when we're doing psychology studies, we need to be cautious about the interpretation of that and whether or not we can generalize to everybody else in the world. Independence. Do not break this assumption. If you violate this assumption, your study is gone. It is donezo. There is nothing you can do. All right. If somebody's scores are impacting somebody else's scores, there's not a way that you can salvage that other than completely get rid of everybody's scores who are tainted. Okay. So independence is not an assumption that we want to violate. Normality. We would say that parametric statistics are very robust when it comes to the assumption of normality. What do I mean by the word robust? Robust means that even if the assumption is violated, the statistic still works out well. All right, and all of the statistics that we talk about, the t-test, the z-test, when we're talking about the analysis of variance later on, all of these are very robust against normality. So even if we have data in the population that's not normally distributed, that it's negatively skewed, or if it's leptokurtic or platykurtic, it doesn't really matter. Okay, our statistics are still going to work out well. And part of the reason for that is that the central limit theorem. So the central limit theorem, the sampling distribution is going to be normally distributed, okay, if we have 30 or more subjects that we're sampling. So if we've got 30 more subjects, we are in the clear. Central limit theorem helps us out again. All right, what to do if we violate homogeneity of variances? More to come about this. We can alter our statistics in a certain way. We're going to talk about this in lab when we get SPSS to calculate independent samples t-test for us, because we can do a lot more with SPSS than we could ever do by hand. All right. Ooh, that's dark. All right, so that's it for this lecture. I hope you enjoyed it or tolerated it, whatever it is that you do, and have a wonderful day. And I will talk with you later.